Thanks, Jennifer, and thanks everyone for being here this morning. I'm going to zoom out a little bit now and talk about the process of putting together a feasibility study report. And so these are my topics for this morning's session. And I have a snapshot here of an oldie but goodie guidance document. This is a classic from EPA. It goes back to 1988, and at yesterday's session in Connecticut, I asked for a show of hands of how many people in the room weren't born yet in 1988. So we'll do this again here. Who wasn't born here in 1988? All right, we got a few. So there's still a lot of excellent information in this document. It kind of outlines the whole process of putting together a feasibility study report. And I'm going to use it for a number of the slides here today. And there have been a few changes to my slides along the way, but as Jennifer said, they'll be updated on the website. So this is a flow chart from the EPA guidance document, and it gives a nice overview of the overall remedial investigation feasibility study process, because the feasibility study fits into this overall framework of the RIFS process. And the process starts over on the far left there with some of the preliminary steps you take when you're first investigating a site. You're doing the initial site assessment. You're looking at the regulatory program that you're going to be in. And then you move on to the work planning phase. And then the process kind of splits into two parallel paths. The remedial investigation phase on the top and the feasibility study phase on the bottom. And I think it's interesting that it's put together this way, in that a lot of the work that goes on in the remedial investigation feeds into the feasibility study, so that it's not necessarily linear. You finish the site characterization, you move on to the feasibility study. Many times it's important to have information coming in from your site investigation, your site characterization, to help inform the technologies you're evaluating as part of the feasibility study. So there should be a back and forth, as shown here on the chart, between the remedial investigation and the feasibility study process. And it also may include some treatability investigations, which there'll be more discussion on later this afternoon as well. But just as a definition, have a definition here down at the bottom of what the feasibility study is. And we're basically looking to come up with the most appropriate remedy based on our evaluation of remedial options and considering risk management decisions as well. And at the end of the process, you come out with a selection of the remedy, and then the more formal process, if there is one involved, with a record of decision, which then allows you to kick off into the remedial design and remedial implementation. So we're going to talking about feasibility study, we're going to use the EPA framework as a basis for the discussion. But as you know, most of the states have slightly different swizzles on how the feasibility study will carry forward, and we'll highlight some of those along the way as well. And along those lines, here are some other versions or names for a feasibility study, depending on what state or program you might be in. In the RECRA program at the federal level, a corrective measure study is also akin to a feasibility study. In brownfields projects, you're looking at an analysis of brownfields cleanup alternatives, or ABCA. In New York, the feasibility study process is called the remedial alternatives analysis. New Hampshire, it's called the RAP. Vermont, it's the CAP. And in Massachusetts, it's the phase 3 and the MCP. And in Rhode Island, for example, the FS is actually part of the site investigation report. So you can see it's all different versions of the same idea of the feasibility study. So we're going to drill down a little bit here into the first box under the feasibility study process, the development and screening of alternatives. And this is broken down, as shown here, into a series of steps. And this, the first step under here, the development of remedial action objectives, That's the process that Nick covered earlier this morning. We'll talk about some general response actions, and then the identification and screening of technologies. Mike's presentation on all the universe of technologies that we have to select from. And then a key part of the feasibility study is combining technologies potentially to come up with an overall site-wide approach for remediation. So in the EPA world, general response actions are kind of broad categories of how to address contaminated media. And the typical big four contaminated media we might be dealing with at a site are soil, sediment, groundwater, and surface water. And typical broad classes of general response actions are things like containment, which might include capping or encapsulation or hydraulic control, removal, treatment, disposal. Again, these are kind of broad categories. The technologies under each one of these categories come as part of the next step in the process. And then lastly, there's institutional actions. These are also classified as general response actions. These could be access restrictions or monitoring types of programs. So in the identification and screening of technologies, what's happening at this step is under each of those broad general response actions, a number of technologies are being evaluated to screen them for whether they will be effective, implementable, and cost-effective, as shown at the bottom. And the resource, Mike pointed out a number of resources for finding and evaluating technologies listed here again as well. And this is just a screenshot from the cluein.org website, EPA's website. They have a lot of different technologies listed here, and you can click on any one of these links and get to a whole series of reports, performance reports, cost reports. It's really an excellent resource when you're investigating a technology that you might not have too much familiarity with, and you can really get back to the basic documents that support it. So this is just a diagram of an overall process of screening technologies for effectiveness, implementability, and cost. And this process lends itself to keeping it kind of in table or figure format without a lot of narrative text. This is an example of screening a groundwater general response action that's basically a pump and treat system. And it's looking at a number of technologies over here. Just my laser is not working so well, but that second column from the left, a number of technologies under the pump and treat option having to do with treatment and discharge of the treated water. And then for each of those technologies, there can be a further division into different process options, things like precipitation or ion exchange, just as a hypothetical example. And then the screening happens across the top there on the top there with effectiveness, implementability, and cost. With effectiveness, at this stage of the screening process, the effectiveness is the most important part of narrowing down your technology list. And costs are just intended to be relatively general, relative in comparison to one another. We're not looking for, fine-tuned cost estimates at this stage. So you go through this screening process and you basically rule out things that are either not going to work at all or they're just way too expensive, and you narrow down into a smaller group of technologies for the general response action that you're shooting for. And so once you have your filtered down list of technologies, the next step is in the FS process is to assemble those technologies that made it through the screening process into a group of site-wide alternatives. And usually these alternatives are set up to provide a range of options for managing different levels of risk. And they should address all contaminated media. So if you've got a site with contamination in soil and groundwater and sediment, there might be different technologies you're going to need to apply to address that site. So your remedial alternatives might include a number of approaches that are slightly different from one alternative to another, depending on which media you're focusing on. Some of the in the EPA world, the typical categories for the ranges are is usually a no action or a limited action alternative. It's no action alternative is really a baseline alternative to compare your technologies or your alternatives against not doing anything. The second broad category is source control, and the third is usually a groundwater plume type or management of migration for groundwater group of alternatives. And if you're dealing with a smaller state site, not in the Superfund program, you probably wouldn't organize it into this group of different categories. But so you're in a smaller site, you might only be looking at 2 or 3 alternatives overall. And in some state guidances and rules, there is only a requirement to not necessarily look at more than 2 alternatives in some cases. But for larger sites, certainly any federal Superfund site and some RCRA sites, you might be looking at something like 5 to 8 alternatives. And the reason is you've got multiple media to deal with. You have a number of different risks that you want to address with different types of technologies to address them. And so once you have your alternatives described, you want to, or identified, you want to describe them to a degree that's sufficient to support a good cost estimate. And usually that means bringing your alternative to the conceptual design level. And a conceptual design typically includes a site layout, how things are going to be laid out in site equipment. If you're doing an injection program, roughly how many injection points you might have, what your major components would be, a process flow diagram, not necessarily design drawings, but enough information at a conceptual level that can support decent estimates of quantities that can feed into your cost estimate. So this is just a hypothetical example of how a site has put together a number of alternatives to address different contaminated media. In this hypothetical example, there's an area of lead contaminated soil here and a TCE area of contaminated soil that's led to a plume in groundwater. So we have 2 really different classes of contaminants. We have a metal and we have volatiles, and we have both soil and groundwater addressed. So obviously not one technology is necessarily going to address everything at this site. So you're looking to combine a range of technologies and put them together. And so across the top here, there's 5 alternatives, and for the media, there's 2 media involved, groundwater and soil. And under each of these 2 media, there's a range of different technologies to address this site. There's also some actions here at the bottom that are common to all the alternatives. These are typically the institutional controls or the administrative controls types actions that would be common to all the alternatives. In this example, there's the no action alternative. And then as you march across from left to right, the combinations get increasingly more aggressive. So in this case, alternative 5 is the most aggressive. It includes things like on-site incineration. That's kind of dating how old this example is. You don't really see that anymore. But the point is that this example is intended to show a range of alternatives from the least aggressive to the most aggressive. So just a quick diversion to treatability studies, because these can be very critical to evaluating the feasibility of a remedial option. And there will be more discussion on these later, and it's important to realize that, as shown in this diagram, this can be an iterative process between the feasibility study and the site characterization, the treatability investigations. You want that treatability investigation information to come in and support your feasibility study and your evaluation of your technology. So it's not necessarily a linear process. You want to have that feedback that you get from evaluating the effectiveness of technologies, sites specific to the site you're investigating. So basically, the treatability studies are intended to reduce some of the uncertainties with respect to performance and cost once you get to the detailed analysis of alternatives. They typically involve laboratory tests or bench tests. They can also involve pilot scale studies. But on the other hand, oftentimes pilot scale studies are taken after the remedy's been selected and now you're moving to remedial design and you need to scale up the technology that you've selected to make it to full scale. Okay, so now we have our alternatives assembled, and the next step is to go through a detailed analysis of those alternatives. And these alternatives are assessed against a set of evaluation criteria, and they're compared against each other, and they provide the basis for selection by the decision makers. And in EPA world, there are 9 evaluation criteria that each alternative is expected to be evaluated against. The first 2 are known as threshold criteria. These are statutory requirements in the CERCLA law. Each alternative needs to address how it will comply with these two top criteria. The next group here is balancing factors. So these are important, but they're not necessarily each alternative has to hit a home run on each one of these. These are where the alternatives start to distinguish themselves from one another. And then in the bottom 2, 8 and 9, these are the modifying criteria. And this is more akin to a public notice type situation where there's going to be community input. If it's a federal site, there's going to be state or regulator input on it. And this is where those entities come in and weigh in as part of the feasibility study on what their preferences are and have their influence on ultimately what is decided. So just drilling down a little bit on what these criteria are, and I will also mention that each state has some states follow the EPA criteria to exactly, and other states have slight differences, and we'll touch on those in just a second. But here are the EPA definitions of each one of these criteria. First one is overall protection of human health and environment. Again, this is a threshold criteria. In the feasibility study, each alternative has to address how it will be protective of human health and the environment. And the second big one is the alternative has to comply with laws and rules. And again, in Superfund world, the acronym is ARARS, which stands for applicable or relevant and appropriate requirements. And then these are further broken down into 3 or 4 different categories. There's the chemical specific ARARS, which have to do with rules and regulations addressing specific contaminants. Groundwater quality standards would be an example. Drinking water standards would be another example. Location specific ARARs have to do with rules and regulations that the alternative has to comply with respect to where the site is or what state it's in. And then action specific ARARs have to do with specific things that are being done as part of the alternative. If it's at a RCRA site, there may be certain treatment standards that have to be complied with, or if there's hazardous waste involved, RCRA standards may apply there as well. And then the 4th bullet is the catch-all. These are the other criteria, advisories, and guidances that every state has in different areas that should be considered as well as part of the evaluation. So again, these are the threshold criteria. You want your alternative to meet these at a minimum. And then we move into the balancing criteria. Third one being the long-term effectiveness and permanence, and the 4th one being reduction of contaminant toxicity, mobility, or volume through treatment, with a preference for permanent and significant reduction. So here are some of the items and points that your feasibility study needs to address under each one of these criteria. and this kind of lends itself to putting it in a kind of a table format. So you can have your table set up with these criteria and have check marks, or you can have little descriptive text in there about how the alternative does with respect to each one of these criteria. Moving on the balancing criteria, there's also short-term effectiveness and implementability. And short-term effectiveness gets to how the community is going to be protected during the remedial action, how the workers are going to be protected, whether there's going to be any potential adverse effects just from the process of implementing the alternative. And implementability is organized into technical feasibility, administrative feasibility, and availability of services and materials. And technical feasibility gets to the ability to construct the alternative, its reliability, its ease of undertaking, and the administrative feasibility gets to the question of what kind of permits are required. Are there going to be access agreements for off-site or abutting properties needed? All speak to the question of whether your alternative is feasible. And then lastly is the availability of services. Are there contractors who have done this kind of work? Are they local? Do they need to be brought in from far away? Is the equipment available? Are there disposal facilities available to handle the types of waste that might be generated? And then the final balancing criteria is cost, and cost is organized into these three categories: capital, annual O&M, and monitoring costs, and present worth cost, which we'll come back to. I'll spend a little more time on cost in a little bit. And then the modifying criteria I mentioned earlier are the state acceptance and the community acceptance. And these again are incorporated not necessarily as part of the FS report as you're putting it together, but after the draft FS has been issued and it's out for public comment, and you're incorporating those comments into the evaluation. This is just a sampling of how some of the states' evaluation criteria compare to the EPA's. The 9 criteria we just discussed are lined up here in this column. And then just a couple of state examples. Check mark indicates that state basically follows pretty much exactly what EPA is suggesting for an evaluation criteria. New York is pretty much right in line with EPA, although on the state level, they include a future land use criteria for evaluation. In Vermont, it's the same thing, but there's environmental impact and sustainability as well. And in Massachusetts, Karen and Marianne are going to talk a little bit more about Massachusetts criteria as part of one of their case studies. So the last step in the feasibility study report is to do a comparative analysis of the alternatives. And this is where the advantages and disadvantages of each alternative are described and assessed relative to one another. It's usually a narrative discussion, or it can be a table discussion of the strengths and weaknesses of the alternative. And usually this is a qualitative assessment. Sometimes there's a desire to want to put some scoring or ranking systems in play, but I would just caution before doing that, because that can lead to some controversy, because it kind of implies a level of accuracy or judgment that might not be warranted given the subjectivity of the relative value of these alternatives. And I'm not aware that any state guidance or rules actually incorporate a numeric ranking system for comparing alternatives, but I'd be happy to hear if others in the room are aware of such a thing. But I don't think any of the NUMOA states have anything like that. So this is more of a qualitative comparison of each alternative against each other. And ultimately, you're looking to identify the preferred alternative based on that analysis. So after the FS is completed, depending on whether the site is a public notice type site, certainly CERCLA sites and RCRA sites under RCRA permits are subject to public notice. In these cases, the EPA or the state agency will prepare a proposed plan or a proposed remedial action plan, and this will go out to the public and it's usually a 30 or 60-day comment period, and there'll be a public meeting along the way, and this is the opportunity for the public to make comment on the remedial alternative. But as I'll get to later in the lessons learned, it's really important to actually get to the public before this happens, because you want to have the public engaged in the alternatives you're evaluating before it's necessarily official. Many of the sites I've been involved in, I've gone through the FS process. It's been very helpful to have engaged the public ahead of the proposed plan or the proposed remedial action plan coming out, so that it's not a surprise. They feel like they've had some contribution or some questions that they could have asked along the way, and that their input has been considered is putting this feasibility study together. So once the comments come back, then the state or the federal agency puts together the record of decision, which is the decision document, which is basically your kickoff, your official okay to start the remedial design and get into the remedial action. For sites that are not subject to public notice, and certainly sites that have the LEP or the LSP program, Massachusetts, Connecticut, New Jersey, it's really up to the licensed professional to select the remedial alternative, and there won't be a public component to that, and there may not even be a state component to that unless the site is audited. So that's kind of the FS process, and I'm going to just go into a few different paths off of that process. The concept of presumptive remedies. These are intended to help streamline the formal FS process, given whether a site has contaminants or conditions that have been readily treated with certain technologies that have been effective before. There's a big caveat to using presumptive remedies, and that can be that you can get too much confidence that a presumptive remedy is going to work. It's very important to still have all that site characterization data that you need to select an appropriate technology. And just because a presumptive remedy may be recommended for your class of contaminants and your type of site, it doesn't mean that you don't need to do a thorough job of site characterization to support your remedial design. But you should be aware that these presumptive remedies are available, and EPA has come out with a number of them. And again, the intention is to streamline the FS process and kind of take out some of the high-level coarse screening of technologies that you would otherwise have to do. So it eliminates some of those steps from the formal FS report. And this is just a table of some of the EPA presumptive remedies for different types of sites and different types of contaminants. The VOC, just as an example, the VOC class of contaminants, SVE and multi-phase extraction are clearly the presumptive remedies in those situations. And I have some references here and some links to, if you're interested in more information on the EPA descriptions of presumptive remedies. This is the document for multi-phase extraction. And these are just some screenshots of some of the other presumptive remedies that are available. But again, caution when using presumptive remedies, it doesn't eliminate or obviate the need for good site characterization and leading to good remedial design. And in addition to the federal level, there are also some states have their own presumptive remedies. This is an example from New Jersey. It's a presumptive remedy for soil contaminants at schools, child care centers, and residences. So it's very prescriptive. It's a very narrow situation. Actually, this table goes on quite a bit more. I just picked off a screenshot of a portion of it. And it's very prescriptive. It gives you two options for addressing historic or contaminated fill in these types of settings with the usual types of barriers and demarcations. So if your site's in this type of a situation, this can easily streamline your FS, and you're basically narrowing down very quickly to what your approach is going to be. I'm going to turn to cost estimates because they're a very important part of developing a feasibility study. Like it or not, oftentimes a remedy selection comes down to cost. and so it's important to have a good basis for your cost estimates. And this is another oldie but goodie classic guidance document from EPA. It's on developing and documenting cost estimates during the feasibility study. And I think it's probably the best cost estimating document out there in terms of giving you a framework and a format for consistently putting cost estimates together. So I have a few examples from this. This is, I think, a pretty cool chart from this guidance document. It kind of shows how the level of cost uncertainty is really wide at the beginning of a project when you're just at the beginning of screening of alternatives, and that the intention of going through the RIFS process is to narrow down those costs as you go along the way. And when you're at the FS level, at the EPA's expectation at the FS level, you're getting to a point where you're at an accuracy of plus 50 or minus 30% of actual costs is where your estimate should be. So this is kind of an order of magnitude cost. And then as you move forward in the process, you get to final design. Your remedial alternative is going to be more defined, and hopefully you'll be able to get a better cost estimate. Your cost uncertainty window narrows considerably. But that's what we're shooting for at the FS level, roughly, is that plus 50 minus 30%. So the key components of an FS cost estimate, the big three, are the capital costs, the annual operation, maintenance, and monitoring costs, and the periodic costs. And periodic costs are those things that happen every few years, not necessarily every year. It can be things like major equipment replacements, 5-year reviews in the Superfund world, and final site closeout. So when you're putting a cost estimate together, just some basic steps of what to do. Obviously, you want to have the alternative well described with the major items. Basically a conceptual design fleshed out to a level sufficient to support a cost estimate. And then contingencies are always an important part of feasibility level cost estimates to account for the uncertainty that you still have at the FS level. Professional and technical services come in as well. And then lastly, you calculate a present value. And the point of the present value is to try to compare apples to apples. You're getting all your alternatives on a common metric, which we'll look at in a second. So this is just an example of a capital cost presentation. It includes line items for capital cost items. It provides a subtotal, and these cost estimates are usually built up from the bottom. You're starting with the construction cost, and then you're adding your contingencies and your professional and technical services later. Again, this is an FS level cost estimate. There may be, and it's a guidance, there could be other ways to do this, but this is a suggestion, and if you follow this, it will give you a consistent framework for your cost estimates, and you want to have that consistency from alternative to alternative in the FS process. I'll just point out that the contingency here is defined. It's actually has two components. There's a scope contingency and a bid contingency, and the scope contingency speaks to the uncertainty and necessarily exactly how your alternative is going to be implemented. You still don't have a final design yet. There may be still some things that are going to change in your alternative as part of the final design that provide that contingency. And then the bid contingency has to do with you're just not sure what market conditions or economic conditions are going to be at the time that the remediation is implemented. So that bid contingency is intended to cover that. And then the professional and technical services are there at the bottom. And the easiest thing to do is to apply percentages of the costs above that to get to those costs. And there are some guidances on what to select for percentages. There's some nice tables in this guidance document on it's not necessarily use the same percentage for each alternative. It depends on the technology you might be using. For example, a soil excavation contingency might have a much broader contingency because there's more uncertainty about how much you're going to have to dig out, depending on what your post-excavation samples may say. Other alternatives that are more straightforward, like a capping alternative, your well-defined limits, your contingency there might be much smaller. And then for your professional and technical services, There's a sliding scale here that's suggested depending on what your overall capital cost is, your different types of professional and technical services, the percentages to apply for those services are shown here in this table. Again, these are suggestions. You don't have to use this, but if you're going to use something, just make sure it's consistent and you have a nice reference to go to provide the basis for your estimate. And then you put this all together in a table that shows the overall capital costs, annual O&M costs, and present worth costs. In this table, for example, year 0 is the capital cost, and it's a 10-year alternative, and you've got your annual costs here and a couple of periodic costs. And then you apply your discount factor to get to your present value. The discount factor is basically the interest rate minus the inflation rate, so it does account for inflation. And it basically is the amount of money you have to invest today to have enough of an income stream over the lifetime of the alternative to fund the annual O&M and the periodic costs, and of course the initial upfront capital costs. And this is a table of just kind of rolling everything up into a nice summary. If you've got 4 alternatives, you want to compare the costs for each one against another. It's divided into the three bigs: capital, annual, and total periodic. And the present value is shown here in the bottom. And in this example, you can see how the present value of these 2 alternatives, 3 and 4, are pretty much identical. So your decision, if cost is going to be one of your primary decision criteria, you might be interested in drilling down to see how much upfront money that has to be applied. In this case, alternative 3 is less costly upfront, so there may or may not be a reason to default to that alternative. Of course, there could be other criteria that are more important. It's just an example of how organizing your costs this way can help highlight some of the differences between the alternatives and the relative merits of spending more money now or spreading it out over a longer period of time. And to get cost estimating information, this is the Federal Remediation Technologies Roundtable website. They have a series of cost and performance reports for a number of technologies. Some of these are admittedly dated, but they're a good place to start. If you have no other place to go, this is a good place to at least get started. I also mentioned, obviously, the vendors are experts in their technologies. If you have a specific technology you're interested in, obviously talking to the vendor is going to give you your most reliable information. So just 2 more slides. Just talk about a little bit about public perception during the FS process. We touched on it a little bit earlier. Effective communication with the public is the key to smoothing out the process where the public is heavily invested in a particular site. For states where there's public notice or the state agency is more involved in the remedy selection, meeting with the regulator early to discuss potential remedial alternatives before formally launching the FS process can be a very important thing to do to get on the same page, at least understand where each side is coming from, and putting that time up front before you've invested all the effort into a feasibility study, and then finding out later that the public or the state really wanted you to look at this and you haven't done it. So you want to establish whether the project requires public notice and set a schedule for that happening. And then a community relations plan is also important. It can be either a formal plan or an informal plan. Some programs obviously require a formal plan, like the brownfields programs, federal brownfields programs, many state brownfields programs. And here's just a list of some of the elements that you can include in a community relations plan. I wanted to highlight that second arrow, project website and or Facebook page. We're seeing more and more responsible parties setting up these kinds of situations rather than having document repositories or mailing lists or fact sheets. They may still have that stuff, but instead of mailing them out or sticking them in a library somewhere, they post them on the internet, and that is a good way to show transparency and openness with the public and keep them up to date. For sites where there's going to be a public meeting involved, my experience is to be careful with the open town hall style meetings where somebody's up at the front presenting and lecturing, because I'm sure you've all seen how those can go. You get one or two ambitious or eager people to take over the meeting, and there's a lot of people there that are there in good faith, and their voices can't be heard because you have one dominant person. So one way to potentially address that is to break people up into smaller groups and set up sort of a science fair situation where you have a series of tables with maybe some posters and walk them through the process you've gone through to investigate that site and come up with an alternative. And then if you do have one of those people, they are at least contained to that smaller group. And actually it makes them feel more, we all feel more comfortable speaking in a smaller group of people than in front of a large group. So that can be helpful. There's lots of good guidance documents too on community relations plans as well. So my last slide here is just some general lessons learned, having gone through the FS process and under a different number of programs, including the Superfund program. Where you can, if you're in a state where you can get the regulator involved early in the process, that's can be very helpful to having them part of the team. FSs can become long-winded documents, but they can be streamlined quite effectively by using tables, charts, and figures to present your information. So you can avoid those long, this 3-inch binder type of reports. Part of that is keeping the number of alternatives to a minimum. Specifically, some of the states only require 2 alternatives be evaluated, and that can be perfectly good for a small site. Some larger sites might need more. If you can use a presumptive remedy, that would be great. Just be cautious. That doesn't mean you can't stop thinking about how it's going to work. You still need to bring in all the important information to assess that remedy, site geology, the site characterization, etc. To get up a good cost estimate, you need to flesh out the remedial alternative in sufficient detail to support your cost estimate. And as I said, the EPA cost estimating guidance document is a good reference to have a consistent format for presentation. And then lastly, like I said earlier, engaging early in the process with the community, with the regulator as a partner. If you can do that in the state you're in, that can be a very effective way to managing public perception. So thank you very much.
Great. Does anybody have any questions for Dave or any comments on your experience with feasibility studies? Go ahead.
Okay, for the feasibility study part, is there a rule of thumb in terms of what the cost of that portion of the project is relative to the overall plan? Like 10%, 5%.
Is there a rule of thumb for what the FS will cost over the entire, as compared to the entire project cost from site care? I know, does anybody know? I guess, I mean, I think it would depend on the size of your site. Certainly, in my experience with Superfund, it's going to be a large percentage of the cost. But for smaller sites, you probably want to keep it in the single-digit percentage range. I mean, it's my opinion, you want to invest your money in investigating technologies, doing feasibility studies, treatability studies, good site characterization, and not so much on the paper evaluation. So that's just my opinion.
Okay, oh, Fred? Mm-hmm.
Tends to minimize long-term costs.
Yeah.
That question.
So Fred's asking about the discount factor, and EPA's example here is 7%, and nobody's going to get 7% interest. But so I believe in EPA world, it's still promulgated that you have to use the Treasury Department's publicly noticed interest rate. And I think that's actually come down to like 3%. So, but you'd have to have a discussion with the people evaluating it to make sure that's appropriate. We were told flat out when clearly 7% wasn't appropriate that we had to use it, even though market conditions said it should be like 2 or 3%. So for non-federal sites, we certainly will use a more reasonable type of a discount rate, something like these days, 2 or 3%.
Good point. So I guess that's to remember, the higher the interest rate you're assuming, then that's less emphasis on what the actual O&M might be. So it's really beneficial as regulators out there to make sure the interest rate that people are using is lower and more realistic, not 7%. Okay, anything else? All right, well, thank you again, David.